Namaste. Welcome to distance education program of PABSON in Janata Television. Today, grade 10 science we are going to discuss. And in previous class, we have discussed about the acceleration due to gravity that we discussed in the previous class. And shortly, we have derived the acceleration due to gravity also. So today we will continue this class with the acceleration due to gravity. So let's start this acceleration due to gravity. And previously we have defined this acceleration due to gravity also. The acceleration produced in the freely falling object by the shortened force is called the acceleration due to gravity. Only the one force should be involved on there, which is called this acceleration due to gravity that we have defined in the previous class. So, and we have also derived shortly the formula for this acceleration due to gravity, that is z equals to z m by r square. This also we have derived previously, the formula for this acceleration due to gravity, that is g equals to capital G capital M r is by r square, that we have derived in the previous class. Now the symbol for representing this acceleration due to gravity is small g, and the unit of this acceleration due to gravity is meter per second square. So unit of z is meter per second square. So one representation is this one. Another we can represent this by meter per second square. So both we can use for representing the unit of this acceleration due to gravity. And the average value of this acceleration due to gravity of Earth is 9.8 meter per second square. That is the average value of acceleration due to gravity of Earth. And Moon 1.67 meter per second square, and the Jupiter is 25 meter per second square. So they are the average value of acceleration due to gravity in the different planet. Okay. Now one question. So what do you mean by acceleration due to gravity of Earth is 9.8 meter per second square? What do you mean by acceleration due to gravity of Earth is 9.8 meter per second square? So how to define this? Let's see. So we have the formula acceleration equals to velocity by time. This is the formula for the acceleration. And acceleration due to gravity, we will replace this a by g. So how we can define this? The acceleration due to gravity of Earth is 9.8 meter per second square, is the velocity of freely falling object increased by 9.8 meter per second in each second. That is the meaning of acceleration due to gravity, 9.8 meter per second square. So once again, the velocity of freely falling object increased by 9.8 meter per second in each second. That is the meaning of acceleration due to gravity of Earth is 9.8 meter per second square. Now about this acceleration due to gravity, this is produced on the freely falling object. And previously, the people, they used to believe that the acceleration of freely falling object are depend upon the mass. The Aristotle is the person who believed that the accelerations of freely falling object depend upon the mass. That means the bigger mass, more acceleration, and the smaller mass, less acceleration. Previously they used to believe that. But later on, by the Galileo, he concluded that the accelerations of freely falling object does not depend upon the mass of the falling object. What that means is, if the object is very bigger in the nature and the smaller in the nature, both fall simultaneously due to the same acceleration due to gravity. That is conclusion of this Galileo. That's why to make proof of this statement, he performed the experiment on the Leaning Tower of the Pisa, that you can see on the screen also, right? So there is given the Leaning Tower of Pisa, that Galileo, he has proved the experiment on this, and he has proved that with the help of the two object stone, one of bigger masses and another one is the smaller masses. When the bigger masses object and the smaller masses object, they led to fall from the of this. Then he found that the both small stone and the large stone strike on the ground on the same time, which conclude that the acceleration due to gravity of freely falling object is independent on the mass of the falling object. But when the feather and the coin led to fall from the same height, then in that condition the coin will strike on the ground first, and the feather that later on it will strike on the ground, that one, right? And what he concluded from that is due to the presence of the air resistance on the feather. More cross sectional area is there. Due to that more cross sectional area, more air resistance act on that, and due to that air resistance, the feather strike at the ground later on than the coin one. So let me show the one demonstrations here. That is independent on mass. Acceleration due to gravity is independent on mass. So this I have the two identical sheet of papers are there. Identical sheet mean mass also same and the dimension also same, right? So if I squeeze this, so this one I have made the squeeze this, right? So this one is the sheet and this one is the squeezed one paper. The mass is similar one. And if we let to fall this both object from the same height, then okay, let me try this. So watch carefully. Is that possible to see or not? So whenever I let to fall this both object from the certain height, then what conclusion we can see? So let's check. Okay, so whenever I let to fall this, then we can see there the squeeze one paper that fall first than the sheet of paper, though their mass are similar one. That's why the Galileo, he concluded that the acceleration produced on the freely falling object that does not depend upon the mass of the falling object. And later on, by the Robert Boyle, he concluded or he performed the experiment to support the statement of the Galileo, which is known as the feather coin experiment. Okay, so what is that feather coin experiment? Is that feather coin experiment is the experiment which prove the Galileo's theme for the conclusion of the Galileo theme. So what is this feather coin experiment? Let's see. So Robert Boyle, he took the long tube, long transparent tube, okay, and there is presence of one tube which is for the vacuum, also for evacuating this tube, right? Another one is the sealed one. So he kept the one coin and the feather inside it. So coin and the feather is kept inside it. So initially it contained the air. Okay, initially it contained the air. So whenever this device is inverted one, then it was found that the coin will strike on the ground first and the feather slowly strike on the ground when there is a presence of air. Again he inverted this in presence of air, the same result he found. And later on the air from this device is extracted one with the help of a vacuum. That means the air present inside this device is completely removed. And after that, if when this device is inverted one, then it was found that the coin as well as the feather strike on the ground on the same time. So that's why the result of this one is the acceleration due to gravity of this coin and the feather, they are independent on the mass if there is no presence of air resistance. That is the result of this feather coin experiment. And from this result, the conclusion was drawn is the acceleration due to gravity of the freely falling object is independent on the mass of the freely falling object. So that is the conclusion of feather coin experiment. Okay, now let's check So we have derived this relation also, that is acceleration due to gravity g is equals to capital Z capital M by r square, right? This derivations we have done previously also, where this g, small g is acceleration due to gravity, this capital G is gravitational constant, and this M mass of the heavenly body, and this r is the radius of the heavenly body. Now this acceleration due to gravity, sorry, this capital G, that is gravitational constant, this g is gravitational constant, gravitational constant, that means the value is constant everywhere, right? This M is the mass of heavenly body, mass of heavenly body, and the mass of heavenly body, for example, mass of the earth is constant, right? Similarly, mass of the moon also constant, mass of the Jupiter also constant, that's why this mass of heavenly body is also constant. So if this both parameters are constant, then can we conclude from here that z is inversely proportional to the square of radius, isn't it? So this g, acceleration due to gravity, is only depend upon the radius of the heavenly body, not on the mass of the freely falling object. It doesn't depend upon the mass of the freely falling object. So this one is the theoretical proof of this feather coin experiment, that the acceleration due to gravity is not depend upon the mass of the freely falling object, it is only depend upon the radius of the heavenly body. Due to this reason, the acceleration due to gravity on the different places on the earth is vary. What I mean is the value of small g vary from place to place due to this reason. Okay, so the shape of earth, it is not completely sphere, right? It is the oval in the structure. So this is earth, it is not completely sphere, right? The radius of this one, it is called the equatorial radius, and this equatorial radius, so I will represent this by r equatorial radius, and this radius, it is called the radius of polar region. So whenever we check these radius, then the radius of equator or equatorial radius is greater than radius of polar region, right? So we are going to demonstrate that why the value of acceleration due to gravity varies from place to place. So I have already said this g is inversely proportional to square of radius, right? It is dependent upon the square of radius. Now the value of acceleration due to gravity on the pole is more than the acceleration, the value of acceleration due to gravity at the equatorial region. What I mean is, if I check the value of g here, the value of g here, this is the acceleration due to gravity at the polar region, and this one is the acceleration due to gravity at the equatorial region. So if we check the value, then the value of acceleration due to gravity at the polar region is more than the equatorial region. Why the value is more here? So let's check. Okay, so this acceleration due to gravity is inversely proportional to the square of radius. That means this inversely proportional means if radius is more, what the inversely proportional mean, that we are going to discuss. So if the radius is more, then the value of g will be less. Inversely proportional mean, that is value of g is less, right? Similarly, if the radius is less, then value of g is more. That is the meaning of inversely proportional, right? That is the meaning of this inversely proportional. Now look at here, this is the radius of earth in the polar region, right? And when we check the radius of the earth in the polar region, then the radius is less. It is a block-on one, right? The shape of earth is not completely sphere, that is block-on one at the equatorial region, and the thinner on the polar region. That means the radius of polar region is less. Less mean radius is less here. This one is the radius is less, mean the value of acceleration due to gravity is more. Yeah, that means due to this less radius on the polar region, the value of acceleration due to gravity is more. Similarly, the radius of equator, right, or the radius of equatorial region is more. That means radius is more on the equatorial region, so the value of g is less at the equatorial region. So due to the change in the radius of the earth on the polar region and on the equatorial region, the value of acceleration due to gravity is vary. So more in the polar region and the less in the equatorial region. And the value of this one is the acceleration due to gravity at the polar region is 9.83 meter per second square, right? And about this equator is 9.78 meter per second square. So remember this value, the acceleration due to gravity at the polar region is 9.83 meter per second square, whereas in the equatorial region is 9.78 meter per second square. So if the question is there why the value of acceleration due to gravity at the polar region is more, then you can explain in terms of this statement. Clear? So you can explain the radius of polar region is less, due to which the acceleration due to gravity is more, as the value of acceleration due to gravity is inversely proportional to the square of radius. So remember this. Okay. Okay. So this we have discussed one. Now after this, so let's see the one numerical problem belongs to this one. Okay, so calculate the acceleration due to gravity. Okay, before that, let me explain one more thing here. What is the variations of acceleration due to gravity with the height? So let's check that. Okay, variations of acceleration due to gravity with height. So what that means, let me draw the figure. Okay, so this one is earth. It is earth, right? And the object is here, which is at the height of h from the surface of the earth, right? So this is the radius of the earth. So we can draw the distance from here also, no problem, right? Now what is the acceleration due to gravity when the object is at certain height from the surface of earth? So let's calculate the formula for this one. So I have said this is the object which is at the certain height h from the surface of a earth. So here distance between them d equals to r plus h, right? So we have the formula g equals to capital G capital M by r square. This is the formula when the object is at the surface of the earth. When we put the object at the surface of earth, then the formula for calculating the acceleration due to gravity is this g equals to capital G capital M by r square. Now we are taking the object at the certain height from the surface of earth. So let's check for this one. So here the distance between them. So distance between them, okay, if I represent this d, then that is r plus h, that is the distance between them, right? Then mass of heavenly body, so here is earth we have taken, so mass of earth is, let's say, capital M, right? And let's say the mass of small object, we can take small m, no problem, but directly I'm deriving from this one. So let g dash be the acceleration due to gravity at height h. Okay, so g is the representation for at the surface of earth, and g dash is the acceleration due to gravity at the certain height. So when the acceleration due to gravity is there at the certain height, then we will represent this by g dash. So the formula will be g dash, so instead of g, g dash, because it is at the certain height is there, is capital G as it is capital M, right? That is the mass of heavenly body or earth, and instead of radius, the total distance is r plus s. That's why this is r plus s to the whole square. So this is the formula for calculating the acceleration due to gravity at the certain height. Now what is the relations of these two? Let's check. Okay, relation of z and z dash. Okay, so we have g equals to z m by r square, this is equation 1, and g dash equals to z m by r plus s to the whole square. Okay, these are the two formula that we have derived previously, right? So we are going to calculate what is the relation of this g and the g dash, the relations we are going to calculate. So dividing equation second by equation 1, then we will get this g dash by z equals to z m by r plus s to the whole square, whole divide z m by r square. So I have divided this equation second by equation first, so we will get this one, right? Now let's change this 4 layer into the 2 layer, that is, or g dash by z equals to, this numerator is as it is, that is z m by r plus s to the whole square. Numerator is as it is, and the denominator is just reverse of this one, that is r square by z m. So this 4 layer that change into the 2 layer, right? So let's simplify this, or this gm and gm cancel, that means g dash by z equals to r by r plus s to the whole square. So here is square and here is square, so I have include this on the same bracket. So one more step here, or z dash equals to r by r plus h to the whole square into z. So this is the relation between g and g dash. That means acceleration due to gravity at the surface of earth and the acceleration due to gravity at the certain height. That is the relation between this two. Okay. Okay, similarly, so this one is the relation. Similarly, if we take the object beneath of the surface of the earth, what I mean is, if I dig some certain hole and put the object here, suppose here is the object, then what will be the acceleration due to gravity on this condition? Let's check. Okay, so let's suppose this g dash, at this place the g dash, at this place acceleration due to gravity is g dash, right? And at the surface of earth z. Okay, and the mathematical relation for this one is g dash equals to 1 minus d by r into z. This is the mathematical relation. Okay, this you will derive in the higher classes. Only the relations we will discuss here. So what is this d mean? It is the depth of the object from the surface of earth. Okay, so this d is the depth of the object from the surface of earth. So this is the relations at the when the object is kept below the surface of the earth, right? Now one more thing here. So if the object is exactly at the center of earth, what will be the value of acceleration due to gravity? Let's check. So what I said, the object is exactly at the center of earth mean the value of d is equivalent with the radius of the earth, right? So what I mean is, so g dash equals to 1 minus, so this d and the radius of earth is similar one. That means we can replace this d by r by r into z, right? So this and this cancel, g dash equals to 1 minus 1 into z, or z dash equals to 0 into z. Therefore the value of acceleration due to gravity at the center of the earth is 0. Acceleration due to gravity at the center of earth is 0. The questions may be there, at which place of the earth the acceleration due to gravity is 0, then at the center of the earth the acceleration due to gravity value is 0. And why the value is 0, I have derived this one. So you can follow this procedure for answering the question why the acceleration due to gravity value is 0 at the center of the earth. Okay. Now so let's check the differences between the capital G and the small g. Okay, this capital G, differences between capital G and the small g and the capital G. This small g, it is the acceleration produced on the freely falling object, and the capital G, it's a universal gravitational constant. Okay, this one is the acceleration produced on the freely falling object, and this capital G is the universal gravitational constant. That means the value of this g, it vary from place to place. For example, previously also we have discussed the value at the polar region and the value at the equatorial region, they are completely different, isn't it? But this capital G, its value is constant everywhere. Wherever you check the value of capital G, that is the constant everywhere. And the unit of this small g, it's a meter per second square, and the unit of this is Newton meter square per kg square is the unit. This one is meter per second, and this one is the Newton meter square per kg square. Okay, and the average value in the case of earth, its small g value is 9.8 meter per second square for the earth, and this value is 6.67 into 10 to the power minus 11 Newton meter square per kg square everywhere. Wherever we check, then the value is this one. Okay, so today we have discussed this acceleration due to gravity, and some derivations we have done, and we have derived the formula that g equals to z m by r square. This formula we have derived previously also, and we have revised this also. Similarly, g dash, we have done this g m by r plus h square. This also we have derived today, and also we have derived the relation between these two. This also we have derived, and one more formula we have learned is g dash equals to 1 minus d by r into g. So these things today we have learned. In the next class, there's some numerical problem related to this we will discuss. So this much for today. Thank you very much for joining the class. Thank you very much.